Hi, my name is Martin. I'm a postdoc at Harvard University. I am going on the job market this fall, and I made this video to explain a bit about my research. So I finished my PhD from University of Copenhagen 2 years ago under the supervision of Lars Hesselholt. So this is my website, and here is my email address. Feel free to send me an email. So to situate my research, I decided to make this triangle of ideas. So my main research area is algebraic K-theory. So throughout here, X is going to be a scheme, or probably it's going to be affine throughout, but it could be very general. And so that's the top of the triangle is algebraic K-theory, and the other corners are topological Hochschild homology. And down here we have the p-adic cohomology theories, so coming from number theory. So I'm thinking of things like crystalline cohomology and de Rham cohomology and so on, and prismatic cohomology. So the way this triangle works is that from K-theory to THH, there is a trace map, as it's called. And this map has helped facilitate many computations in K-theory over the years. Along the bottom of the triangle, THH relates to the p-adic cohomology theories in many different ways. The one that I'm thinking of here is the recent work of Bad, Morrow, and Scholze. And so what they realize is that you can filter the left-hand side, the THH side, give filtrations whose associated gradients are expressed in terms of these p-adic cohomology theories. So another way of saying that is that you get spectral sequences from the right-hand side computing the left-hand side. So I think of this diagram as like a commuting triangle, and so putting these two other sides together, you should get spectral sequences that compute K-theory from these p-adic cohomology theories. So I'm going to express this diagram through three types of questions, all of which focus on the case of singular schemes. Three questions in K-theory. So these are classical K-theory questions. The first one is nil-invariance. So this is asking, for example, whether or not the K-theory of a truncated polynomial algebra, let's say truncation degree E, whether or not K-theory sees this extra nilpotent information. Similarly, you could ask about excision in K-theory, and so this could be exemplified by asking, for instance, whether or not the K-theory of the coordinate axes in the plane is the same as the K-theory of just the base point. So here, geometrically thinking of these two axes here, and since they are topologically contractible, you might hope that K-theory doesn't see any difference here. Similarly, again, there is the question of A1 invariance in K-theory. So this is the question of whether or not the K-theory of the polynomial algebra agrees with just the K-theory of the base. So for all of these cases, the answer is a resounding no. So K-theory is not does not give an equivalence between these. So none of the questions that I asked are true. But we can use this triangle of ideas to actually understand the failure of these questions. So this is exemplified by the following theorem of Hesselholt and Madsen. So they take K to be a perfect field of characteristic P, and they look at the truncated polynomial algebra and the K-theory of it, and they find that in odd degrees, this is given by some explicit expression involving the Witt vectors of the base field K. They have to mod out certain Verschiebung elements. But the main point here is that it's a very explicit formula. These are very understandable groups on the right-hand side. So in the paper that I call 1 here, I'll give references at the end of the talk. In this paper, I give a new and a simplified proof of this result of Hesselholt-Madsen. And my work relies heavily on the recent work of Nicolaus and Scholze, which clarified the lower left-hand corner here, the THH side of things. So using that work, I was able to give a new proof of this result. And so in the excision type setup, I have a similar similar in spirit calculation. So this is in the paper that I'll cite as 2. And again, let K be a perfect field of characteristic P. So I'm looking at the coordinate axes over K in many variables. So here, let's just draw the 3-dimensional case. And again, looking at the K theory of this ring, and I give an explicit formula in terms of the bit vectors of the base ring. So it's slightly more complicated than the above formula that we saw, but it's very similar in spirit. So it's some big product of finite. It's a big but finite product of finite length bit vectors in the base ring K. So the way these results work is you use this triangle of ideas. First, you use the trace map to reduce to a statement inside the THH world, and then you use the relationship to p-adic cohomology theories, which is why you see these bit vectors showing up. Yeah. So in the third question, so this is the question of A1 invariance. Let me first recall a theorem of Quillen, which says that in case you put a regular ring inside K theory, then the K theory of the polynomial ring and the K theory of R just give you the exact same result. But this is not true in general. And to study it, we define the NK spectrum. So this is a classical construction going back to work of Bass. So it's just the fiber of the map that sends T to 0. And in current work in progress together with Eldon Elmanto here, we give an explicit formula for these NK spectra in the case of R being a finite dimensional Noetherian K algebra. So K here is again a perfect field of characteristic P. So our formula is expressed in terms of the Bad-Morrow-Scholze motivic complexes, typically denoted ZP of J. The value is in R here, so J is greater than or equal to 0. And the way our result is that we have a filtration coming from the work of Bad-Morrow and Scholze on the P completion of these NK spectra. And so the graded pieces, let me just write like this, the graded pieces of this BMS filtration on NK R P completed is given by the fiber. So the formula gives it in terms of the fiber of a change of topology map from the Zariski cohomology of these motivic complexes. There's a shift here. So first of all, from the Zariski cohomology and then to the CDH cohomology, again with coefficients in these motivic complexes. So that whole thing, we tensor it with a specific group or module, WK module T of K, where T of K is a fixed p-torsion-free WK module. So we're currently investigating this formula and consequences of it. And this is something that I'm very excited about. I also have various other projects you can read about in my research statement. But I think this is all that I wanted to say for now. So thank you very much for listening. And here are the references. Thanks.